In studying star formation, it's hard to get away from what are considered two fundamental questions. One is how fast star formation takes place, and the other is what is its end product. So these are big questions, but they're not the only questions, and as we go along in addressing these questions, we actually encounter a lot of other fascinating theoretical and observational issues. So, yesterday I talked about one of those big questions, and today I'll talk about another of them. So on Monday I talked about star formation rates, and I talked about the star formation rates as averaged over large scales in galaxies. And I argued in favor of a kind of self-regulated picture of the interstellar medium and star formation. So today I'll be talking about smaller scales, and what I'll be talking about is really towards the question of what sets the end product of star formation. Here, though, I would say that the theoretical issues are in some ways more complex, and I think that the picture is more incomplete, although people have different opinions about this. And however, in the last, I would say about 15 years or so, there's been a lot of progress in understanding the processes that take place within giant molecular clouds, and particularly the role of numerical simulations has been absolutely essential for this. So this is where so much progress has been made in using the numerical methods that you're all learning about at this summer school. So I think, though, that there are still a lot of, now we've kind of gotten the field up and running, and there's a framework in place, and it's really the field where there's great opportunities for young theorists like yourselves to make a big impact, because by no means are all the important questions answered. And I'll try to convey that to you in the next hour. So what's the end product of star formation? Well, the end product of star formation is stars. And the most basic description of a star, the most important property of a star, is its mass. And this mass defines its place on the main sequence, which is determined by the many processes within the star, in particular the nuclear properties, the dynamics, the internal dynamics, and flow of radiation. And that also determines the end of what happens at the end of a star's life. Does it explode as a supernova? Does it, or not? Does it just die out slowly? And so the distribution of masses of stars, the distribution into low mass and high mass, really then affects very much what happens in the life of a galaxy. In particular, this affects what happens to the interstellar medium, which I talked about yesterday, because the energy from massive stars is very important to the life of the interstellar medium and to the formation of new stars. So if you had no massive stars, then that would make things very different. So it's been known essentially forever that low luminosity, low mass stars are much more common than high luminosity, high mass stars. And this was first quantified by Ed Salpeter, and here's the abstract of his paper from 1950, I think 1954. And so this is really, this paper is a classic. I guess it's 55 actually published. This paper is a real classic in astrophysics. It's one of the, there are more than 4,000 citations to it. It's the 15th most cited article of all time in ADS. And actually, if you don't include the papers that are about methods or that are really physics papers, there are some physics papers in there also, then it's in the top 10. So this is clearly one of the most important papers, and that's because that's telling you that the IMF, the distribution of stellar masses, is a very important property in describing stars. Okay, so this is what Salpeter found back in 1955, and here's his power law, where the distribution of stellar masses, dN/dm goes as the mass to the minus 2.35, or this is dN/d log m, goes as minus 1.35 at high masses. So where are we now? Well, so of course there's been a lot of work on this since 1955. And particularly in recent years, it's been possible to extend down to low masses, in particular to the hydrogen, below the hydrogen burning limit, so into the brown dwarf regime, below 0.08 solar masses. And the IMF has been fitted in a number of different ways. There's no theory for what the IMF should be in terms of its shape, but it's been fitted in a number of different ways. So one way that is commonly used is the Krupa 3-part power law. Another is a log normal at low masses plus the power law, which is essentially what saltpeter found at high masses. And there are also more complicated functions like the one that's shown here, which is log normal, and then 2 power laws, which is shown in this from this review. So here, this shows a compilation from this review of Bastien et al. Of a number of recent observations of the IMF. And so there you can see that at the high end, they're generally consistent with a power law. And in particular, they're consistent with the power law that saltpeter first identified. These are all in the Milky Way. There's also, you can see, there's a turnover in low mass. And that low mass turnover is typically in the range of about 0.2 to 0.3 solar masses. And so this is something that is often characterized as a universal IMF. But looking at it, you can see that it's consistent with something universal, but by no means are these all identical to each other. You can see clear variations. And saltpeter actually said, he was a little bit disappointed by the fact that all of the observed distributions of stellar masses are consistent, at least, with a universal IMF. He basically thought that this had held theory back, because if the observations are not pointing towards differences, then it's very difficult to come up with a theory which says what is, since you don't see parameter variations, then it's hard to come up with a theory that really could kind of explain where the IMF comes from. So saltpeter was disappointed, but in fact, in the last few years, there's been increasing evidence that the IMF does vary. So not so much within the Milky Way or even the local group, but looking further afield, particularly towards massive ellipticals, there's evidence for a bottom-heavy IMF. And that's based on a few different lines of evidence, but one of those is based on kinematics, and I won't go into this in detail, but using these kind of kinematic studies, it's been shown that the mass-to-light ratio compared to what you would get for saltpeter, as you go to more massive galaxies, that's in this direction, that the mass-to-light ratio increases. So a higher mass-to-light ratio means you have more low-mass stars. So this suggestion, based on this method, and there are also spectral absorption line studies that show a similar effect. And they suggest that these most massive elliptical galaxies may have a peak in the IMF that's much lower, perhaps an order of magnitude lower than in the Milky Way. So what's different about these galaxies? Well, they are believed to form stars at a much higher rate and under much higher pressure conditions than in local galaxies. So that may be a hint that something different is happening under very different conditions. And really, I would say that extending beyond the Milky Way to these types of systems, where there were quite different conditions, really may be key to finding different IMFs. And this would satisfy saltpeter's hope of a non-universal IMF. And it also would really help theorists in kind of trying to deduce what actually determines the IMF. However, on the theory side, we can just go ahead and see what we can find using kind of direct first principles simulations and theory to try to understand what would set the IMF. And what are really the key ingredients. So with that prologue, I'll move on to the main part of my talk. That was kind of a motivation for what one of these important big questions is. And what I'll be talking about, this is kind of a summary of where I'm going. And I'll first introduce molecular clouds. And I think you've heard about molecular clouds in some of the other talks so far, and the properties of cores. And I'll talk about classical star formation, and then some of the things that that we have learned in the more dynamic contemporary theory of star formation and how these relate to the classical theory. Okay, so I'll start with molecular clouds. So star formation takes place in objects like this. This is the Orion molecular cloud. And the gas in these clouds is very cold, and it's also very structured. So you can see that structure even in this single, even in this large map, you can see a lot of structure. And this is kind of a hierarchical structure. So on large scales, there are big sheets and filaments. Then within them, there are clumps. And then there are the densest, most embedded structures are cores. So the dynamical properties of these structures vary with scale. So on the largest scale, the clumps and filaments are self-gravitating in the sense that the effective pressure, or the gravitational energy density, is much larger than that of the surrounding diffuse ISM, and I talked about that yesterday. When you get to somewhat smaller scale, then there are clumps and filaments which are probably transient. That is, they don't have pressures much higher than the surrounding molecular cloud. And then the very dense cores are, again, self-gravitating. So these clouds are turbulent, and the turbulence is really their outstanding their property. And if you look at the turbulence in clouds, you look at this scale and then this scale and this scale, and as you go to larger scales within any individual cloud, or if you look at a small cloud and a bigger cloud, they have what looks like a roughly universal relationship where the turbulence increases as the 1/2 power of the size scale. And that's shown here in these based on CO observations. So since the velocity dispersion is increasing with scale, there must be some scale at which the velocity dispersion is low enough that it is sonic. And you can go down to where the sound speed is about 0.2 kilometers a second. So the corresponding scale is about 1/10 of a parsec. And so that is what we call the sonic scale. Below that scale, the turbulence would be below the sonic speed, and therefore you would expect turbulence to be less important. The turbulent pressure is lower than thermal pressure, so turbulence would become unimportant at scales smaller than that. So this line with size relation, this power law going as the 1/2 power, is consistent with what we call the Berger's spectrum. And the normalization, if a cloud is gravitationally bound, should look like this, so that the velocity dispersion on the scale of a whole cloud would be proportional to the surface density of the cloud and the cloud size. And then going to smaller scales, the velocity dispersion would scale with the size of the cloud. And simulations do reproduce the observed velocity scalings and relationships. So in simulations, starting from the very earliest simulations we did, quite some time ago, let's see if we can, oh, doesn't want to run. There it is. So you can look at it in 3 dimensions. So in highly turbulent systems, high density post-shock structures develop because of the turbulence, because there are strong shocks. And these compressions and rarefactions, because they're independent, will tend to produce a log normal density distribution, which is as shown here. And the mean value of the log of the density, or the dispersion in this distribution, these are related to each other. And that distribution changes as you change it depends primarily on the Mach number of the turbulence, where the value increases logarithmically with the Mach number. So that means that in a cloud that has a higher velocity dispersion, a higher Mach number, there will be the mass-weighted density will be higher and compared to the mean density, and also the volume filling factor will be lower. So there's a Mach number dependence that affects both of those at the same time. And you can see it's actually easier to see the log normal of the column density, because that's very directly measured using extinction measurements and other things. And you can see examples of this here. So one of the things that turbulence does is, of course, it creates density structure. And something that's important to keep in mind is because the power of the velocity spectrum is increasing towards large scales, therefore, the power of the density structure also increases towards large scales. And so, you see large-scale structures, and those are the most prominent in a cloud. And that has the important implication that the star formation then will tend to be clustered because it occurs, it's correlated on the large scales. So it's not dispersed uniformly through a cloud. Now, looking at clouds, and particularly in more recent observations like those of Herschel, you can see this kind of filamentary structure very clearly, and you can also see that the star formation is lying along these filaments. And so here, this is the Taurus cloud, which shows, you can see the stars which are lying along these filaments, and particularly the youngest stars are closest to the center of filaments. These are different sources here, including the T Tauri stars and younger stars, and I won't go through this in detail, but the youngest ones are most closely aligned with the filaments. And that's true also for this cloud. So this shows both the stars and cores. So the green is class 0 protostars, and the blue are prestellar cores. Okay, so you can see this filamentary structure on large scales and smaller scales. And one of the things that's been done recently with Herschel data is to use curvelet decompositions to define the filaments within the cloud and then to measure the widths of these filaments. And so the size scale is interestingly close to the sonic scale. So it's close to about 1/10 of a parsec. And some people have suggested that this is kind of universal. I don't think there's strong evidence for it being universal, but the scales are comparable to that sonic scale. Yes? They do show up in the surface density maps, but the thing is that there's a projection, right? So you're projecting. So it's basically just a way of, it's kind of an unsharp mask. So it's a way of bringing out the structure. But it's there. So it's just one of many possible ways of identifying filaments. Okay, so the width of filaments is, there are filaments down to quite small scales in clouds. Okay, so what about cores? Well, cores are the objects that actually are going to form stars. And molecular cores are identified in a number of different ways, including using tracers of dense molecular gas, and this is something that Stella talked about, how you would in your simulation make a simulated observable in these kinds of molecular tracers that could then be compared to clouds. So another way, in addition to molecular tracers, is from continuum, and that's when you're looking at dust. And again, Stella talked about how you can take your simulation and produce a mock observable, which would then be similar to what is observed in continuum. And shown here is a particular cloud, the Pipe Nebula, with cores, the positions of cores overlaid on top of the extinction map of the whole cloud. Okay, so what about these cores? Well, and here is from a Herschel study of the Aquila cloud. This shows the positions of cores. I think they found more than 500 cores in this entire map, and just in this part of it, there are, I believe, 450 cores, and so you can see this subfield here. And most of these are gravitationally bound. If you actually look at their gravitational energy and their thermal energy, they're gravitationally bound cores. So these cores, as identified, are a large fraction of them are likely to become stars. So in addition to the fact that these tend to lie along filaments, you can start to ask, well, what is the distribution of masses of cores? Because if they're likely to become stars, then it's a quite interesting question. What is the distribution of these prestellar objects? And one of the things that's quite intriguing is that this prestellar, the mass distribution of cores is actually quite similar in its shape to the mass distribution of stars. It's just offset towards larger masses, and it's offset by about a factor of 3. So this is, however, for, this cloud is only about 10,000 solar masses, so this is not a really massive cloud. Most stars actually form in much more massive clouds than this one. But if this holds up in looking at the typical clouds, then that would suggest that understanding the core mass function will take us a long way towards understanding the mass function of stars. So this makes this something that's very interesting to study and to understand. Now, the fact that, so if it turns out to be true, still there's this factor of 3 shift towards lower masses and going from cores to stars. And so here's for Orion. Again, a similar thing is seen. This is a more massive cloud than Aquila. So again, a similar thing is seen here. So what about this shift from the core mass function to the stellar mass function? Well, in part, this must be due to the processing that takes place when you form a star disk system. And one of the things that happens is that the disk drives a powerful wind from the disk and from the interface between the disk and the magnetosphere of the star. And that wind, you can see the effects very clearly. So here's a jet in the center, and depending on whether the star is still embedded or not, this may be seen in optical or infrared. So there's a jet in the center and then a surrounding molecular outflow. And much of the mass, on the order of 3 times the mass that actually ends up in the star, can be removed by this wind. And the wind basically sweeps up a large fraction of the core and carries it away. So that may explain the offset between the core mass function and the final stellar IMF. Okay, so coming back to the details of cores, what are their properties? Well, if you look at them in detail, not just their masses, but if you look at individual cores, they can be mapped. And one of the things that you can get out of a map is what is the distribution of density in the core. And this shows for cores that are mapped in millimeter continuum. This is in arc seconds, but these cores have radii, so this scale is about 0.03 parsecs. So this is very high resolution. And you can see these profiles, there's the dots are from the observations, and this is fit very well by an isothermal equilibrium, which is a Bonner-Ebert sphere. And so these cores are centrally concentrated, and their profiles are fit very well to what you'd expect theoretically. So why isothermal? Well, the temperature of the gas is actually fairly close to isothermal. And the other thing is that because the scale is small, these are actually, they have very low internal turbulence. So for these same cores, this shows the internal velocity dispersion. And this line here is the sound speed. So basically, the turbulence in these low mass individual cores are either subsonic or generally transonic or subsonic. And that's the case for these cores at all scales within them. This is at different scales. So these cores are characterized as being centrally concentrated and having subsonic internal turbulent velocities. Now, another thing that you can do is you can ask how long do they live, and that's a statistical question that you can address by counting stars or cores at different stages. So if you count the number of T Tauri stars of known ages and then the number of prestellar cores, that will tell you the lifetime of the prestellar stage and also the protostellar stage similarly. And doing that tells you that the prestellar phase has generally a lifetime of a few times the free fall time at its own mean density. And that prestellar phase, the lifetime of the prestellar phase is also comparable to the lifetime of protostars. So that is when the star is still embedded in its surrounding core. Okay, so looking in more detail, so here's an example of a velocity-coherent core, and this has also been studied at very high resolution with a with the GBT and then with EVLA. And this velocity-coherent core, actually, if you look at it in more detail, you see this filamentary structure. And this filamentary structure, this shows the velocity dispersion up here. And the velocity dispersion, the upper line here, hard to see, is sonic. So this is basically, the velocity dispersion is half of sonic in this structure. And the profile here of this filament here is fit very well by what you'd expect for an isothermal filament. Okay, so I've talked about what GMCs are and their filaments and cores. And now let me move on to what's kind of the classical theory of star formation, which is looking at collapse of individual cores. So the classical theory is you have an isothermal sphere, and the maximum mass that can be supported by thermal pressure is the critical, misspelled here, Bonner-Ebert mass, where the formula is given here in terms of the pressure at the edge, or in terms of its internal sound speed, the thermal speed, and the density at the edge. And if you put in numbers for this that are comparable, typical of actual observed cores, that gives masses that are comparable to observed stellar masses. So this makes a lot of sense comparing the theory with observations. And here, cores that are less concentrated than this critical one are stable, and more concentrated than this are unstable, where the critical is a factor of 14 density contrast between the center and the edge. Okay, so we expect that anything that's unstable could not last a long time. Something has to happen, and what happens is that it collapses. So that's basically what would happen if the mass exceeds the maximum or critical mass. And this was first studied by Richard Larson in the late 60s. And he kind of indirectly answered the question. He was not initially looking at these Bonner-Ebert spheres, but he just looked at the collapse of what was initially a spherical density region. And what he found is that essentially the density starts to increase, and it approaches this power law profile. And it's in such a way that this shows from later simulations by other people, that the nature of this collapse is that it starts in the outside and it works its way in. And so initially, the outside has a low velocity, and then a wave of collapse starts, and it works its way inward. You can see this wave of collapse. And eventually, it approaches this power law. So that is, this shown down here is later work by Foster and Chevalier. And so you reach this critical Larson-Princeton solution, and Larson and Princeton showed that you can have a self-similar solution that approaches this asymptotically. So what happens after you reach this kind of power law asymptotic profile? Well, the next thing is something that was studied by Frank Hsu, which is a rarefaction that propagates outward. So first, everything collapses and you get this very steep density profile, and then there's a rarefaction where gas that's on the inside basically accretes onto the star, and you have a wave of rarefaction that propagates outwards, where the time scale, and basically the reason it propagates outward is that the time scale is shortest in the central region where the density is highest. So that collapses first, and you have a collapse that's going outwards. So basically you start with this profile and you work your way down to less and less dense profiles. And the velocity in the interior is basically free fall, and the density has an r to the minus 3/2 power law. So that is the classical solution for core collapse. Now, this is isothermal, so it's very simplified. What about the real case? Well, including more physics, this is from one-dimensional radiation hydrodynamic simulation, so including the chemistry, including the radiative transfer. The first stage is this isothermal collapse. So this is density and temperature. Then when the central core, a central core will develop, which is optically thick. And that, when it's optically thick, it's no longer going to be isothermal. So that's the first core that you can see. And the temperature, instead of being isothermal, is now higher because heat has been trapped. When the temperature reaches about 2000 Kelvin, the molecular hydrogen will dissociate, and this allows, because it's endothermic, it allows further collapse to occur. And so you get this second collapse stage here. And then finally, the dissociation is complete, and the second, what's called the protostellar core forms, and that's the center here, the highest density. And actually, this is remarkably anticipated by, this is much more sophisticated recent work, but this was anticipated. You can see this profile, and then you can see what Larson was able to do in 1969. So I think great credit to Richard Larson for really anticipating that. He's kind of almost prophetic that he was able to do this using the methods available at the time. Okay, so that's what really happens at late stages. Of course, this is the spherical case, and the spherical case is not the real case. So in reality, there's rotation, and what that rotation does is it produces, the angular conservation of angular momentum tends to produce a disk. As matter falls in, it spins up, and then this disk can accrete inwards. Now, one of the things that happens is the magnetic fields will apply magnetic braking. These magnetic torques will tend to make the gas lose angular momentum so that it doesn't want to form a disk. And a very active current research area is understanding how this collapse occurs and whether the combination of ambipolar diffusion and various forms of resistivity are sufficient to break the to allow the magnetic field to decouple from the matter so that a disk forms. Now, we know that disks do exist, so this isn't, it has to work out, and in some sense this is a theoretical problem that needs to be solved in order to understand how disks form, because disks indeed certainly form. Okay, so classical theory and its contemporary updates considers the evolution of individual cores. You have a core, you see what happens, whether it's rotating or not, whether it's magnetized or not, it will collapse, and it follows that evolution. And in fact, observed cores are similar to those that are modeled in this classical theory. You can see, again, here some profiles which show that the core density profiles are very well fit by these static equilibria, with masses that are quite reasonable compared to stars. But this classical theory has a big missing link, and that is, what is the origin of these cores? Where do these cores come from? Why do they have the masses that they have? Why do they have others of the properties that they have? Like, why are they so quiet? Why is the turbulence in their interiors so low, given that they're created in these highly turbulent clouds? There's the question of how, if you look at a whole cloud, how does the properties of the cloud determine the distribution of core masses? So the classical theory and its modern updates are great, but they leave a lot of questions unanswered about the properties of individual cores and the distribution of properties of cores. So now let me move on to a little bit of what many people are working on at present. So by including the process of core formation, we can try to address these kinds of questions. Why are they so quiescent? What sets the distribution of masses? And so let's still stay as simple as we can and think about, do a little bit more, but say, how do you make a core? After all, you have a cloud that has supersonic turbulence. So if you just consider the most basic question of, if you have a supersonic flow, how do you create a core in a supersonic flow? Well, the simplest geometry would be spherical. So let's consider the spherical case. And what's shown here in the movie is, as a function, this is radius, that's velocity and density. And this just is set up by having a supersonic spherical inflow. And what happens is that a shock will form. You can see the shock here. And the shock, there's a density jump here. And inside that shock, the velocity, you can see the velocity here is very low. So the post-shock velocity will be subsonic, basically because the velocity decreases by 1 over the square of the Mach number. So over time, the shock moves outward. You can see the shock moving outward here. And as the shock moves outward, more and more mass will be in the post-shock stage, so it will be at high density. And it gets to the stage where the mass is sufficient that it will be gravitationally unstable. At the point that it becomes gravitationally unstable, you can see in the movie that it then undergoes the same kind of collapse that occurs in the classical kind of starting from a static core, the same kind of classical collapse. That first it collapses from the outside in, and then what's not shown here is that there's infall starting in the center and then working its way out. So this accretion of the envelope. And the simulations show that the timescales are such that the time when the core is supercritical is comparable to the time that the infall, the duration of the infall. And those are both quite short compared to how long it takes the core to build up. You could see if you were watching the movie, it took a really long time before anything interesting happened because it's building up the core for a long time. And so the features of these very simple simulations actually tell you a lot about, real cores, even though they're quite idealized. So one of the things is that it does evolve to this asymptotic profile, which is exactly the same as the Larson and Princeton found from their self-similar theory, where the density goes as 1 over r squared. And the way that it reaches this is from this outside-in wave of collapse. And so, actually this was anticipated by Larson as well. What he suggested is that the collapse should eventually approach the same behavior in all cases, regardless of things like the initial density. So, again, he anticipated this, even though he didn't do simulations of this kind. Okay, so this actually kind of says something interesting about a number of the features of observed cores, including why are they so quiescent? Well, they're quiescent if they form in a shocked region because a shock makes the velocity decrease by a large factor. Also, it says something about the timescale. So why are there a comparable number of protostars and prestellar objects? Well, because those timescales you expect to be similar based on the collapse solution and the accretion. And so it says something interesting, and why even in a more realistic case where we're looking at the formation of the core, not just its evolution, why cores do have these observed properties. So this is all, though, quite idealized because realistic flows are not going to be spherical. So looking at this in a more realistic, but still not completely realistic context, we can learn more. And why don't you jump directly to something which is incredibly realistic? Well, one reason is that you don't have as much control over those kind of simulations. So it's still very informative to do controlled simulations. And the controlled simulations that I'll say a little bit about are where you impose an inflow. So there's a converging flow, and it is turbulent. So it has the characteristic turbulence that would occur on this scale, but it also has an inflow as you would get in some part of a cloud where you have a large-scale converging flow. And that large-scale converging flow is making a shocked ribbon or a shocked piece of a shocked sheet, which can then collapse. So I'll talk a little bit about some simulations where we do controlled simulations where we vary both the turbulence level and, in particular, consistent with inflow velocity. So we're looking at how do the properties of the cores depend on the inflow Mach number. Okay, so here's a movie. So this movie is a Mach 5 inflow simulation, and you're looking at it projected face on. And structure grows, so this is turbulent, but structure grows first on large scales because the power spectrum increases towards large scale and because gravity prefers large scales. So we did a number of simulations in this study. This is the lowest Mach number, just over 1, then higher Mach number, so Mach 5 and Mach 8. And you can see that the structure that forms depends on the Mach number. So that's because at higher Mach number, there's more turbulence, and therefore more structure is created. The time for the first collapse depends on the inflow Mach number, and this is scaled relative also to observed cloud properties of the relationship between density and velocity. So one of the things that you see in these more realistic simulations is you still see the approach to the Larson-Princeton asymptotic profile. You still see collapse starts on the outside and works its way in. You still see the power law profile develop. And this is the Mach 1, and this is the Mach 4 simulation. So you can still see for the individual cores that form, they still have the same behavior as in the classical theory that was developed in the 60s. Now, other properties of these cores are also interesting. So one is that the cores and also the surrounding filaments are velocity-coherent. So you can define cores. Here they're defined using the gravitational potential, which is a much better defined way to define a core than just to pick a given density threshold. And then you can look at both the mean velocity and the velocity dispersion. And you can see that everywhere there's a core, there's a low velocity dispersion. So these regions are coherent in the sense that observers use that the turbulence level is low. Now, something that's kind of interesting is that even the not strongly self-gravitating regions like these filaments actually have low velocity dispersions as well. That's for two reasons. One is that they are formed post-shock, so they do tend to, the velocity decreases in forming them. And another is that essentially because you're fixing on a small scale where the density is high, because velocity dispersions increase with scale, you will preferentially have a lower velocity dispersion. And remember that this is exactly what's seen in the observations as well. Okay, so coming back to the observations of filaments, this is the distribution of the velocity dispersion, and these are generally subsonic, as I mentioned before. And another thing that you can look at is the mass per unit length. So you can define a filament that is hydrostatic equilibrium, and there's a maximum mass per unit length of about 15 solar masses per parsec if the sound speed is 10 Kelvin. And so these, if you look at the mass per unit length, that's similar to that theoretical expectation in observed cores. Okay, so now let me say a little bit more about what the simulations say about the relationship between star formation and filamentary structure. And this is ongoing work, so very recent work, so I won't say too much that is quantitative. I'll be talking in a more qualitative way. But I think it will give you a good sense of the types of things that happen. So what's shown here is filamentary structure, and then each of these is a sync particle. And Robi Banerjee tomorrow will tell you more about sync particles and how they're implemented in Flash. We have a somewhat different implementation that we used in Athena. So why do we use syncs at all? Well, we introduced syncs so that we can follow evolution over long time scales. If you didn't put a sync in, then there would be a very steep density gradient. As I showed you, the density approaches an r⁻² power law, and that would become unresolved. So you wouldn't be able to resolve it. And basically the simulation would grind to a halt. And that, even if you add many levels of AMR, you still have this, essentially you would end up having a protostar, which you then can't simulate the rest of the cloud. So we introduce syncs so that we can, look at more than one core and look at the as many cores continue to develop. And so I won't talk in detail about our sync particle implementation. It's similar but slightly different from the one that's in Flash. So one reason that you can be confident about doing this is by testing. So you can test to make sure that the evolution still follows what it would follow if you had not introduced the sink. So for example, we test using the Larson-Pennstone solution. Does it follow the Larson-Pennstone solution? That's over here. It does approach that. And then does it follow the Shu self-similar solution at different stages as mass is accreted during that rarefaction as the rarefaction wave propagates outward? And one of the other things is that because do you have a question? I can't hear you.
Are you doing this in Cartesian?
Yes, this is Cartesian. Yep. So because the Larson-Pennstone solution is basically, you always get it, it's a dynamical attractor in that sense. That tells you that you know when you need to introduce a sink particle, because you introduce a sink particle when you've gotten the when it's approached the Larson-Pennstone solution, and therefore you know that it is properly collapsing. And the other thing about the Larson-Pennstone solution is that the velocity becomes supersonic near the center. So if it's supersonic, then you can be guaranteed that if you introduce a sink, the information from that supersonically collapsing region would not be propagating back out to mess things up on the rest of the grid. So you can be confident about introducing sinks under those conditions. Oops.
How you control the density in the center of the
Just a second. Let's see if I can bring my presentation back. Say again.
How do you control the density in the central region? It doesn't go up?
Well, we introduce the sink, and then so in our implementation, we basically have a sink region. And so let me see if I can bring this back. Hang on a second. Okay, so the sink region is basically, our sink region is 3 zones across in each direction. And it's in our implementation, it's internal boundary conditions. So what it means is that you do an extrapolation from the surrounding active zones into the sink region. And what we do is then we increase the mass and the momentum of the particle is updated according to the fluxes from the Riemann solver at the surface of the sink region. So the mass is removed. Basically, these are internal, it's an internal boundary condition, so those zones are always reset, just like any other boundary conditions, using the active zones. But the mass and momentum are augmented using the fluxes at the interface. Does that answer your question? Okay. Okay, so let's see if I can actually show you again. Okay, so this, here's a simulation of one of these converging flows. This is a Mach 8 converging flow, now with sink particles, and you can see that filaments form, and within the filaments there's localized collapse and we introduce these sink particles are actually bigger than the region, just so that you can actually see them. And you can see that they continue to accrete, they interact with each other, and they continue to accrete gas from their surroundings. So Moonan, who's here at the workshop, hi Moonan. So Moonan is working on this project, and I think she'll be giving a talk where she'll talk about a little bit about what she's been doing on this. She's doing a full parameter survey to understand how the properties of cores depend on in particular, we're looking at the dependence on the Mach number, because everything else kind of can be characterized in terms of this Mach number. So Moonan will talk about her simulations and how she does it and what she's learned so far. So I'll leave that for Moonan. One of the things, though, that you can see is that these cores, if you wait a long time, will basically eat everything that's in the simulation. So that's because we have not put in this. So we haven't put in any feedback from these cores. And without feedback, basically everything would end up collapsing into a star. And I talked about some of the effects of feedback on large scales yesterday, and there are also effects on smaller scales within clouds. So I won't talk about that in detail. But you can see, observers see nothing but feedback, of course, because they're looking at radiation. So we see the effects of feedback, and it's a very active interest of many people to try to simulate this in increasing accuracy. So one of the things that we've been doing recently on this is we've implemented a new algorithm for doing radiation hydrodynamics, and I'll show you some early results from this. So what's shown here is a cloud which is 1 million solar masses, and I'll run the simulation. Good. Okay, so this is turbulent, and the turbulence creates structure the way it always does, and then some regions collapse. These are not individual stars, but these are small clusters, and the color scale here is showing you what the mass is. So these are actually star clusters. Now, over time, you can see that the gases actually starts to be expelled from the simulation. So that is the effect of radiation pressure, which is not shown here. The force on the gas is just proportional to the radiation flux and to the opacity, and that basically drives much of the mass out of the simulation domain. So the same thing now without radiation. It's turbulent, and it will form these sink particles, which are clusters, and these all interact with each other. But just as in the individual converging flow that I showed you, they're just going to eat all of the mass. Some of them will be flung out of the simulation, but they basically will eat essentially all of the mass that's in the simulation. And you can see the comparison here. So this no radiation is showed with solid lines. So with no radiation, this is the gas mass over time. All of it is used up. The stars are the green one. So that's this, as more and more of the mass gets locked up in stars, this is increasing. On the other hand, with the radiation feedback, let's see, so the gas is now this one, so that's similarly declining over time. But now the stars are only a quarter of the mass in the simulation is consumed by stars. So the radiation pressure is able to remove much of the mass in the cluster for this simulation. And we're studying this. We're doing a parameter with Aaron Skinner. We're doing a parameter study of this to understand what the range of efficiencies can be when this is the only feedback that is acting. So, I've only been going for 3 minutes. I think that must be the restart. Let me say a little bit more about star formation in filaments. So coming back to the question of why are there filaments at all? Well, there's a number of reasons that there may be filaments in clouds. One of them is due to shocks. So suppose you have a converging flow and it shocks. Then the post-shock scale, you have some flow that comes in. The post-shock scale will just be equal to the pre-shock scale times the ratio of the densities, and that's just an expression of mass conservation, as you all know. Then if it's unmagnetized, or if the flow is close to being along the magnetic field, you can use the shock jump conditions to express this density ratio in terms of the inflow velocity. And then, how does that velocity depend on the pre-shock scale? Well, there's a line width size relationship. So between v squared goes as L, so you can put this in, and that ends up telling you that the post-shock scale would be equal to the sonic scale in the cloud. Well, the sonic scale in the cloud, if the cloud is in virial equilibrium or scaled relative to virial equilibrium, you can write like this. And for clouds that have typical surface densities of observed GMCs, this scale is about 1/10 of a parsec, as I mentioned back in the beginning. So there's a sonic scale that you would expect to get. You have a flow, and regardless of whether the pre-shock scale was big or small, the sonic scale is what you'd expect for the post-shock length scale that you would get from some converging flow that shocks. So if you looked at this edge on, then you would tend to see something that has a scale similar to this. And that would tend to, it would look relatively filamentary. So that's one reason you might see filaments. Another is because of self-gravity. And so a self-gravitating layer, you can write twice the thickness of the self-gravitating layer in terms of the surface density of that layer. And for typical surface densities that you'd see in clouds, that's about, it's 0.05 parsecs. So then once you have this layer, it can have gravitational instability develop within it. And the minimum wavelength is, again, scaled relative to this thickness. So it's just pi times this number. So that's 0.15 parsecs. So the scales that you get from looking at either shocks or from gravity produce filaments comparable with properties or thicknesses comparable to what you'd expect from physical considerations. And so if you have a filament that's something that's become concentrated and reaches an equilibrium, there is this maximum mass per length, which you can write in terms of the sound speed and g, and that's the number. And that's comparable to the mass per unit length of observed filaments. And again, here's some of the observations. So coming back to this big question, what about the IMF? Can you understand what sets the IMF in clouds? And this shows a few recent results from simulations, one from Matthew Bate using SPH and one from Krumholtz et al. Using their AMR simulations. And this movie is from Bate, which shows, I don't have the details of this here. I guess it's a 500 solar mass cloud, which is turbulent and about half a parsec in size. Now this starts from very high density, and this is a beautiful simulation, and it produces quite interesting results. Here's the distribution of masses and compares very well to the observations. But you have to ask yourself, how did this concentration at density of 5 times 10 to the 4, how did it get there? So we're basically, the answers from simulations are very interesting, but they're not telling us the whole picture, because it's not telling us how this concentration of gas got here without already fragmenting. So that's a very important question for the future, is to really understand how these concentrations of gas form that then fragment to make stars. And so the distributions of core masses and star masses in the simulations that have been done do compare very well to observations, but there's one thing that's missing is a true parameter study, and another is really understanding the initial conditions for how these clusters develop. Do they form by multiple fragmentation along filaments that then concentrates together? How do they really form? So that's something that hopefully someone here will do for their PhD thesis. Okay, so that's kind of gives you a flavor of where the simulations are. What about the theory? So again, this is very challenging to understand the fundamentals of what would determine both the high-end slope and then the characteristic scale in the IMF. I would say that the high-end slope, it's suggestive of a coagulation or fragmentation processes, but I think that there's no completely satisfactory theory to date. What about the peak of the IMF? Well, here we can at least say something just essentially based on dimensional analysis. So if you use the Bonner-Ebert formula, and for the pressure, instead of using a thermal pressure, you use the characteristic turbulent pressure in the cloud, then that will depend on the cloud surface density. So you can plug that into the standard Bonner-Ebert mass formula, and that gives the Bonner-Ebert mass in terms of the surface density of the cloud and the thermal sound speed. So putting in, again, reasonable observed numbers, that gives a mass scale which is comparable to the masses of observed prestellar cores, where the peak of the core mass function is. So I think that this is very suggestive and interesting. And one of the important points is that observed clouds in the Milky Way don't have a relatively small range of surface densities. So that might tell you, that might be saying something about why the IMF seems to have, when observed, a characteristic peak that doesn't vary too much. On the other hand, in these very massive galaxies, the properties of clouds might have been, when they form stars, might have been quite different, and that might explain why there were differences in the IMF at other times. So this is a very interesting, I would say, question, which is not yet well understood. So from controlled simulations, one of the things that you can do is ask whether this kind of idea is reasonable, and that's something that Moonon is working on. So basically following up some initial simulations that we did where we varied the Mach number, that is, we varied the effective pressure, which is associated with turbulence, and we look at what the characteristic mass is of the clumps that form. And this shows, as a function of Mach number, the characteristic mass. And so these simulations was before we had sync particles, and so the characteristic mass is kind of between the late time mass that you expect and the mass of the first core, which I won't go into the details there. They have different scalings with Mach number, and I won't go into the details of that. Okay, so one thing that in the last minute I'll say something about is the role of magnetic fields. So I haven't really talked about magnetic fields much, except to say that they cause problems for disk formation. And I won't be talking about this much because Chris McKee is giving a whole talk on this, I think tomorrow. So he'll really fill you in on all of the details. But I'll say a little bit. So if you have magnetic fields that are frozen to matter, then the mass to flux ratio, which you can also write in terms of the surface density and the magnetic field strength, this will be a constant. And that means that the ratio of gravitational to magnetic energy density will also be constant, and this just goes as the square of the mass to flux ratio. So you have a core, and if it starts with some mass to flux ratio, it will start with some magnetic to gravitational energy density, and as you change it, that will always be the same. So that means that if it can collapse, it can keep collapsing, and if it can't collapse, it will not collapse unless you change that mass to flux ratio. So this can be described as a critical mass to flux ratio, and if you look at observed clouds at high densities, they are supercritical, whereas at low densities, it's subcritical. Now, the observed dense cores have mass to flux ratios, which are about 2 or 3 times the critical value. But if you if you use this, if you assume a spherical core, then you can write the critical mass in terms of the magnetic field strength and the density. And the critical mass for pre-core conditions in a cloud would actually be tens of solar masses. So it's a little bit puzzling. How can you form what are observed to be supercritical cores starting from these subcritical conditions? So one way to do this is by ambipolar diffusion, and that's that's kind of the conventional way, is to say that magnetic flux is lost by ambipolar diffusion. For a quasi-static core, though, the time to lose the flux is very long. It's like 10 times the dynamical time. And as I mentioned, cores are not observed to last that long. So that would be inconsistent with observed core lifetimes. So, but that's for the quasi-steady case. What about for the real case in which cores form dynamically, because they form out of turbulent, highly supersonic gas? So schematically, you can imagine, what happens if you form a core by a supersonic compression. Well, one thing is that the flow will not necessarily be perfectly aligned with the magnetic field. But another is that ambipolar diffusion will be different if you have, if you're looking at something that's dynamic instead of quasi-static. So a simple way to look at this is just to set up a converging flow that has a shock, and you can see right away that the mass, this is the ratio of density to magnetic field, which is related to the mass to flux ratio. This is enhanced in the center of the cloud for a short period. So there's basically a transient phase of ambipolar diffusion in which the neutrals would not see the magnetic field. And this is basically governed by the neutral ion drift time. That is, the neutrals won't see the ions, so they don't know that the magnetic field has been compressed, and they don't know that they shouldn't have what amounts to an unmagnetized shock. So initially, you would have what amounts to a very strong shock because the neutrals don't know that there's a magnetic field which is trying to stop them. And so this is a transient effect which could allow you to have a much higher mass to flux ratio than you would otherwise have. Okay, so the timescale depends on the coupling between neutrals and ions. And the higher the ionization, the stronger the coupling, and the closer you'd expect it to be to ideal MHD. So naively, you would expect that then the mass would increase going from the hydrodynamic case to the ambipolar diffusion case to ideal MHD. But that is actually not what happens in the simulation. So this shows for simulations with low hydrodynamics, then low ionization, higher ionization, and then ideal MHD, the masses actually don't really vary very much. So why is that? And this is something that we're looking at right now, but what the answer appears to be that essentially it's, to think about the spherical core is really too idealized. A core will become spherical once it is in equilibrium, but it doesn't start out spherical, and in particular, cores can form by flow along the magnetic field. And that is what happens in the simulation. So the core forms by gathering mass along the magnetic field in these overdense regions. And you can see that in these snapshots here, that the flow vectors are preferentially along the field. So mass is being gathered up along the magnetic field. And that is how it gets to be supercritical, even though if you just measured if you assumed a spherical core under post-shock conditions, that would have a magnetic critical mass of about 10 solar masses. In fact, it forms a core of about 1 solar mass because it gathers enough mass along the field that the density is essentially higher than the average conditions. So by being anisotropic, Stella, I said it, yay! By having anisotropic contraction, it's able to produce a supercritical core which is at lower mass than you might naively think. Okay, so here's the summary. I guess I won't read this whole summary here, but I'll see if there's any questions before we break for lunch. Yep?
In one of your first slides, you showed us that the ion is steeper in higher mass galaxies, or it was like...
Yes, not necessarily steeper. All that can really be said is that it's weighted towards low masses. Yeah.
Is there any explanation for that in general, or in the theoretical picture?
Well, I think that's something that's a really interesting question. So I suggested that perhaps you can understand it in terms of this kind of scaling relation, that if the pressure is higher, with higher pressure, then the characteristic Bonner-Ebert mass is lower. So that's a possibility because these galaxies formed, they are inferred to have formed at much higher pressure. But this is a very much an open question that I think that is of much interest for everyone.
Actually, I want to ask you about that because, as you know, as you point out, in most molecular clouds, sigma cloud is about 100. However, in regions of massive star formation in the galaxy, it's much larger. And if you look at other regions, like, for example, globular clusters around the galaxy, they have surface densities that are much bigger than that, yet their IMF is normal. Right,
but you're looking at the globular cluster after it formed. So this comes back to the question of, a lot of times people do cluster formation simulations. They start with something that has the final properties of the cluster, but is that really the fragmentation conditions in which the stars formed?
Well, obviously for globular clusters, we don't know. For the case of massive star-forming regions, we to do.
Yeah, so
Because
those,
they measure,
yeah.
and they find that the massive stars are forming in regions with much higher success.
Right, the massive stars, but not necessarily, you know, the low mass stars. So I think that there's a lot of uncertainty about the conditions that the details of cluster formation that both, you know, observationally and what will the simulations show when we can do a wide range of scales as we're going to do. Yep.
I just wanted to clarify in the course that we're talking about, you were saying that there's turbulence is outside of that region, so the external pressure would be the turbulent velocity. But in the core, it's all thermal, the velocity dispersion is constant. And so there is this transition from a turbulent medium outside the core to after it collapses, some converging flow or something, then in the core itself,
Yes. So that when you look at individual cores, I don't know if I can find those. It will probably take too long, but yes, that's the. Oops, that was it. Yeah. So this is from the simulations. You can see these cores that have low velocity dispersion in the core, and then the velocity dispersion is much higher outside the core. So that's supersonic. And then that's subsonic within the core. So that's in the simulations, and then again in the observations, the core regions, whether it's a filament or the core itself, a more spherical core, it's subsonic within the core. And yes, so it's supersonic outside, and then it's subsonic in the core. Of course, there are massive, the cores that form, in which massive stars form, are more turbulent, but those are not individual, you know, they have a lot of other structure within them as well. And I think Chris will talk about that. You're also talking about massive star formation, I believe. Yes, so Chris will talk more about that. This is if you look at individual cores that form low mass stars, this is what their properties look like. Other questions? Okay, let's go eat.